Good morning. Welcome to lecture 10. So, recall that in the last lecture, we discussed the matrix formulation for optics. Specifically, we derived matrices for translation and refraction, and we saw how we could use these matrices, for example, to figure out where the image would appear if I had one spherical refracting surface. Right? So we started our matrix formulation to quickly recall with two variables, right, lambda and x, where we called lambda as optical direction cosine and x is simply the height, right? So for example, if I have a lens or a refracting surface, let's say, and I have an object here, right? So let me call this as object O. So if my ray of light is going this way, right, I can draw a line here, and this angle, right, if I call this angle as alpha and this height as x, then lambda, the optical direction cosine, this part, is what we defined as refractive index of that medium times sine alpha, right? Or we also define that as if this angle perpendicular to that is psi, you can also call it as n cosine psi. The psi plus alpha are equal to 90 degrees. So we use this set of coordinates denoted by lambda and x to come up with the matrices. If you have forgotten what we did, I urge you to go back to lecture 9 and look through the videos. But essentially, we derived the matrix for translation. So the translation matrix we got was something like 1, 0, d over n1, and this is also 1, right? Where this d is the distance, right, that the object travels, right? So if we are looking at going from lambda 1 x1 to lambda 2 x2, we're going from this point to this point, then this distance d is essentially x2 minus x1, right? Sorry, it's not x2 minus x1. It is the distance between x2 and x1. x1 and x2 themselves are heights. So if I have this as x1, let's say at this point as x1, and if I'm going here and this height is x2, the distance between these two is d, right? So so we have that distance, right? So I'm going from point x1. X1 again is the height, right? X1 is again the height, and x2 is the height here. So the distance between these two is d. So that's how we derived the translation matrix. Similarly, we also derived a matrix for refraction. The refraction matrix that we derived was something like 1 minus p 0 1, where we called this p as the power, which was equal to n2 minus n1 by r, where r is the radius of curvature. So here notice that in case of translation you have only one refractive index because translation happens only within one medium. Once there is a change in medium, then it would be refraction, right? For example, here I have, say, this surface here, and beyond this, say this is glass, say this is air. Within air you could have translation, but once your light hits this glass surface, then there is a refraction followed by translation, right? So translation as such, we use this translation matrix for one medium at a time, and refraction is at the interface of two media. That's why in power you have two different refractive indices, n2 and n1, whereas in translation you have only one index, right? So based on this, We also looked at how an image forms at a refracting surface, right? And in fact, we came up with the same formula that we derived using ray optics. Particularly, we came up with this formula of N2 by U, that is the, or N2 by V, that is the image distance. Um, so N2 by V is the image distance, minus N1 by U is the object distance, that is equal to N2 minus N1 by R. Right? This is what the relationship that we had come up with based on the matrix method. So now let's generalize this matrix method even more, right? So now if I have, say, a black box system, I don't know what is in that system, but it's a set of lenses and a set of mirrors or different optical elements, and I know that a particular ray starting from, say, here, I know this coordinates as lambda 1 x1. I would like to figure out when it is leaving the system, so this ray is going like this, let's say, when it is coming out, I would like to figure out what are the lambda 2 x2 are, what the coordinates are. So I can in general write something called a system matrix, and the system matrix is usually written as S, which is written as B minus A minus DC. It is written in this format, right? It's not written as ABCD. It is rather written as B minus A minus DC, because we will see why that is, and we will also see why we have chosen negative signs. We essentially have chosen negative signs because it becomes more convenient for the sign convention. So once, if you have a system for which the system matrix is given, then you know everything about that system. You can trace the rays very easily using the system matrix, because all you need to do is, if you have lambda 1 x1, to figure out lambda 2 x2, you basically can get lambda 2 x2 by operating S matrix on lambda 1 x1. So if you have the system matrix, it becomes very straightforward to know how the ray leaves the system, or how the ray is on the other side of the system, right? So now let's use this concept to derive to derive the system matrix for a thick lens, right? So let's take a thick lens. So we have, say, a thick lens. So here we have a thick lens. So this is the thick lens. Recall we did the same thick lens using the rays as well. So we have a thick lens here, and let's call this thickness as thickness T, right? And let's say the radius of curvature for the first surface is R1, and the radius of curvature for the second surface, let's say it's R2, and let's say at a distance D1, we have our object here at a distance D1, so O is the object, and let's say the image forms somewhere around D2, right? So the image, let's say, is somewhere here. So roughly a ray from O is going to go here, right? And I'm drawing the rays just to derive the system matrix. Once you have the system matrix, you don't need to draw rays anymore. That's the whole idea of the matrix method, right? But because we are deriving the matrix itself, we are still using the rays. So now if a ray is going this way, right? If I look at point P where the ray is incident, right? And we can call this, say, as x1, right? And of course this ray gets refracted, So it bends away from the normal, and then it goes and meets the image point here. So let's call this image point as I, and let's call this height as x2. Okay, so and then let's say the refractive index inside is n, right? And then we are going to derive the system matrix. The system matrix, we are going to write it in a form like this: B minus A minus DC. We'll derive what that is, right? But it is very straightforward to derive the system matrix here, right? Because you have the ray coordinates at 2 points, at point P, and let's call this as point Q. So at point P, let's say you have the ray coordinates as the height is x1 at point P. So the ray coordinates would be lambda 1 x1, right? Lambda is the n sine alpha or n cosine psi, and q is lambda 2 x2, right? So we have these two coordinates, and the ray propagating is undergoing two different refractions, one refraction at point P and another refraction at point Q, but in between, going from P to Q, it is a translation. So there is the first refraction is at Q. So we have first refraction, sorry, at point P. Then we have translation. Translation is to go from P to Q. And then we have another refraction, that is the second refraction at point Q. So we know the matrices for the first refraction, we know the matrix for translation, and we know the matrix for second refraction. So we can derive the system matrix by simply multiplying the order in which these happen. So first, the first refraction happens. So I initially have my coordinates as lambda 1 x1. So for the first refraction at P, at point P, I can write the refraction matrix, right? Recall the refraction matrix is something like 1 time 1, this is the power, right? And negative time negative power, this is 0, this is 1, right? That's the refraction matrix. And the translation matrix is 1, 0, distance by the refractive index, and 1, right? So for the first refraction at point P, I would have 1 minus power at the first surface. So I would have power at the first surface. So this is the first surface. So I'm writing it as minus P1, 0, 1. So this is the refraction at P, right? Then between P to Q, I have a translation. So I'm going to use the translation matrix. So the first element is 1, second is 0. This D is the distance between those 2 points between which the translation is happening. So in this case, those 2 points are point P and point Q. So the distance is nothing but the thickness of the lens. So we simply have T divided by the refractive index is n. So I have n and I have 1 here. So this is going from P to Q. And then finally I have another refraction at point Q. So that's going to be like 1 minus P2, that is the power for the second refracting surface, 0, 1, right? So by multiplying, so this is the refraction at Q. So now if I multiply these three matrices, then I should get essentially the total net effect of the lens on the points lambda 1 x1, which would give me lambda 2 x2. So a product of these three matrices would be my system matrix, right? So now let's do this and see what we would get. So here our system matrix is 1 minus P2, 0, 1, 1, 0, thickness of the lens divided by the refractive index, 1, 1 minus P1, 0, 1, right? Again, refraction at P, translation between P and Q, and refraction at Q. So now if I do the math, basically what I'm going to get is I'm going to get 1 minus P2, 0, 1, and here you would get, this is 1. 1 times 1 is 1, 0 times 0 is 0, so I have 1, right? 1 times minus P1 is minus P1, right? And 0 times 1 is 0. T by n times 1 is T by n, right? And 1 times 0 is 0. Here I would have T by n minus P1, minus P1 T by n1 plus 1, right? Then if I multiply these two again, I would get 1 times 1 is 1, minus P2 times T by n would give me minus P2 T by n. Then I would have minus P1, right? Then I would have minus P2 multiplied by minus P1T and 1 plus 1, right? Then I would have 0 here plus T by n. Here I have T by n, and same thing here, minus P1T by n1 plus 1, right? Sorry, I have been writing n1. There is only one refractive index. The other one we are considering it to be air, so n is the refractive index of the lens itself. So that is not n1, that's n. So there we go. So this is the system matrix. Now recall, right, that we represented our system matrix as B minus A minus D and C, right? Now if I want to make an approximation, so this is for a thick lens of thickness T, right? We considered that thickness is equal to T for a thick lens, and that's how we derived this. Now remember, when we did this in ray optics, we did the same thing. We derived the equation for the thick lens first, and then we assumed that the thickness is going to 0 to derive the equation for a thin lens. So for a thin lens, if I let T go to 0, then the system matrix, so this is for thick lens. So the system matrix for thin lens, where I am letting T go to 0, would be, the first one would be just 1, because if T goes to 0, this term would be 0. Similarly here, if T goes to 0, this term would be 0. I still have 1, so I would have negative of P1 plus P2, right? And then here I would have 0, here I would have 1, right? So notice that if I have a thin lens, basically it looks like a refraction matrix. The refraction matrix itself is like this: 1 minus power 0, 1. So here I am getting the same thing, 1 minus something, 0 times 1, right? So this, for a thin lens, looks very much like a refraction, because if it is a thin lens, it makes sense that if this lens is very thin, there is one refraction happening here. If it is very thin, if the thickness is going almost to 0, then there is not much translation here. It immediately goes for the second refraction, right? So you have two refractions taking place back to back if it's a thin lens. So that's why the powers of both refracting surfaces 1 and 2 just simply add up. So the system matrix for a thin lens looks like a refraction matrix, except with a power of P1 plus P2, because you have two refracting surfaces, right? So